Obviously, weather prediction and climate predictions are massive computational efforts. They are numerical models. The first great attempt was made by Louis Richardson in the 1920s, and this schematic has made the rounds. And you can see that he's looking at the globe and pointing at various issues or regions for forecast or whatever. And there are a bunch of people here who are receiving input from people sitting here in this stadium. So he had actually organized people which would compute part of the problem, pass it to the next person. So it was some kind of a cluster with multiple nodes, like a crude supercomputer, which obviously made errors, and it took forever to produce a 4-hour forecast and so on and so forth. But the sheer vision of how ultimately forecast would work is really stunning in terms of its realism, right? Then in the 1940s, the first computer came up, ENIAC. This is Jules Charny. ENIAC led to big dreams about military use, nuclear power use, geoengineering use, but also led to Charny doing some experiments in weather prediction at the same time across the Atlantic. Rossby was doing experiments as well, and GFDL came up with the first coupled model in the 1960s, ocean atmosphere coupled models. All sorts of details had to be added as we went forward. And you probably have seen this kind of a cartoon somewhere or the other already, where we already mentioned that we take the sphere and we split it into these grids in the horizontal and vertical, and then you have to deal with the singularity at the poles for the atmospheric problem, so people end up moving the poles and so on and so forth. And essentially you have horizontal latitude, longitude grids and vertical grids, with all these processes being represented similarly on land and in the ocean. I won't go into the details here, but I think you know what they are. We have briefly talked about them, and we will look at it in different ways here. So numerical weather prediction has evolved. Models have become better, higher resolution. Numerical techniques have evolved in terms of making sure that things like concentration of humidity doesn't go negative, positive, definite methods and efficient methods, efficient computing technologies, parallel processing, all great things along the way. And climate modeling has also evolved parallelly. Typically, weather prediction has been a higher resolution version of essentially the same model, but obviously focused on different timescales and different features and different prediction timescales as well. So in the 1950s, you started to have atmospheric land process models, and then the coupling happened. So you had global scale coupled climate models evolving, atmospheric chemistry, sulfate aerosols, biogeochemical cycles, carbon cycle. Everything was evolving independently. You can see they didn't become part of the climate models till here in the 1990s, 1980s, and so on. Sea ice was also evolving and became part of the system in the 1980s. We have had understandings and modeling evolving for dust, sea spray, carbon aerosols, upper atmosphere, interactive vegetation, which has come much more recently. We talked about aerosols briefly. Now it's a big part of there's a big community on aerosols and their impacts, direct and indirect, as we mentioned. Direct impact on radiation and indirect impact on cloud optical properties, cloud formations, cloud condensation, nuclei, hurricanes, everything else. Okay, so the climate projection business has driven its own agenda as well. If you look at the global climate models in the 70s, they were simple with some representation of carbon cycle and precipitation. In the 1980s, they began to add more details of land surface. Sea ice and land ice were still being prescribed. Well, sea ice models did exist, sorry. Cloud processes got better. The first assessment report for the IPCC, I think in 1992 if I'm not mistaken, used a swamp ocean, where ocean was not dynamically active but just something that was transporting heat. Second assessment added more details. Third assessment, fourth assessment, we have had AR5, and now AR6 is coming out by 2021, maybe delayed because of COVID and so on. Resolutions have increased because of computing capabilities have increased. So far, the first assessment was at 500 kilometers with spectral truncation in the atmosphere at 21, which determines the resolution of the atmospheric representation. So 250 kilometers with double the resolution at T42, to T63 and T106, and now it's getting better and better as computational resources get more efficient. This is a nice list of 20 climate processes and properties that typically need to be parameterized within global climate models. So you can see that radiation, scattering by aerosols, absorption by the atmosphere. I won't read all of them, but you can see that even though we are solving major first principle equations for momentum, energy, thermodynamics, continuity, and so on, there are many processes that are not explicitly solved in terms of primitive equations. So for example, here condensation, and let's say 19 is deep convection, emissions of long wave radiation from clouds, and so on. So this is not to say the models have problems. This is just to say we are using more and more data that becomes available to improve parameterizations and the models and forecast skills and projection skills and the scales at which the projections can be made, not just global means but regional scales and so on. Okay, so that's a brief introduction to the evolution of the models and the weather prediction and climate prediction. We talked about the seamless prediction or unified models, where people don't want to separate the weather prediction model from climate prediction models anymore. And of course, seamless ideas should also go to projection timescales. Different configurations, different resolutions may be still required to be used, because running weather prediction necessarily requires very high resolutions to resolve important features at multiple day timescales, let's say day 1 to day 10. And then climate models have to be run for multiple seasons, and projections have to be run for multiple decades. So obviously resolutions have to be probably reduced, but the details of representation also have to change. Weather models don't need necessarily full coupled models, for example, but climate models do, and climate projections will need anthropogenic forcing of greenhouse gases and aerosols and other human activities that modify land use and so on, right? So dynamic vegetation, for example. So all these sorts of details have to be considered even in the unified framework. But coming back to the weather and climate predictions, we talked about climate prediction as the predictability of the second kind, which means it's forced not only by initial conditions but also boundary conditions, where especially ocean boundary conditions, which are slowly varying, are critical. So coupling either single one tier or two tier forecasts that we talked about. And weather prediction is an initial value problem where initialization is critical, and data assimilation then becomes critical for initialization. So in the next podcast, we'll talk about data assimilation and how that has evolved and has also contributed to expanding the weather forecast skill horizons. Okay, so that goes together with increased data coming in, improved models and improved resolutions as well, and then the data assimilation. And data assimilation itself evolves into coupled assimilation now as well.